Welcome to Unit 23 and 24. This is the highlight of the course, the culmination of everything we have done so far. We have two theorems. The first theorem is Stokes Theorem. The second theorem is the Divergence Theorem. Let's start with Unit 23, Stokes Theorem. Everything we have learned so far comes in here. If a parameterization of a surface, and the parameterization also tells you what is up in that surface. We have also a boundary, we call this C, the boundary curve, and then we have a vector field given. The curl of F, when integrated over the surface, so the flux of the curl through the surface, is the line integral of the field along the boundary. So this looks very much like Green's theorem, which is somehow a flat version of Stokes' theorem, but don't mix them up. Green's theorem is a theorem in 2 dimensions, while Stokes' theorem is a theorem in 3 dimensions. So let's just look at this example. We have a hemisphere, so the boundary is the rim, it's the end of the world, and it's oriented in the right way here. So the surface is oriented outwards, and the boundary is oriented in such a way that the surface is to your left. And in this case, this is the right orientation. So we have already given you here the parameterization of the sphere. It's a standard parameterization of the sphere, and also it's actually a hemisphere, so we go only to pi half. And we have also the boundary curve. This is just a circle, cosine t sine t 0, and it has the right orientation. So let's just compute both sides. So in this case, the vector field had quite a simple, and you can already see that the result will be positive, because now what we do is we integrate over the surface. We go from 0 to 2 pi, and then from 0 to pi half d phi, and then what I have to plug in is the curl of the vector field, which is in this case just a constant 0, 0, 2. And then I have to dot it with Ru cross Rv, or R phi cross R theta. R phi cross R theta I've already computed you here. So we have computed that early on. It's sine phi, sine square phi, cosine theta, sine square phi, sine theta, and then we have sine phi, cosine phi. Okay, let's compute the right hand side of this. In order to do that, I'm using a little trick here. So we can write F as the vector field minus y x 0 plus, and then a gradient field. So what we have is we compute the line integral is closed curve C. That gives us 2 pi. So this is a basic example. It's an example which is not so easy, because we have actually used here also the fundamental theorem of line integral. So I don't know, this would have been probably the easier way to go if you had a choice. But often the flux integral is harder to do. I want to make 2 remarks. We will probably make more in the lecture. So if F is a gradient field, that's a very special case. We have a gradient field, then the line integral along a closed curve is 0. The boundary of a surface is always consists of closed curves. Like here we have one closed curve, another closed curve. Like the sphere is an example of a surface which doesn't have a boundary. And actually that's a special case also. If the surface doesn't have a boundary, that's part B. So we call this surface closed. If a closed surface, there is no boundary part, so the right hand side is 0. One of the nice applications of this whole multivariable calculus is electromagnetism. You don't have to be a physicist to appreciate light, right? So this is an absolutely amazing thing that you have things like light. You can generate light from motion. From light you can generate back motion. Fluid dynamics is also a place where this formalism comes in. For electromagnetism, it's just nice to formulate these Maxwell equations, which are magically describe interaction of magnetic fields. Magnetic is B, and the electric field E. So there are 2 equations which deal with the divergence. So the first equation tells you that the charges are sources for the electric field. And similarly, that's actually the same equation which also appears here in Gauss, when for gravity, the mass density is a source for the gravitational field. So it's an absolutely fantastic way to describe this. It actually implies Newton's law. And here, this actually implies, just with some manipulation, that the fields in vacuum just move along waves. Maxwell was motivated by fluid dynamics. He kind of thought in terms of fluids, and was exposed to Stokes Theorem as a student. You know, he had to take an exam, and one of the problems was to prove Stokes Theorem. So nowadays we teach it, but at that time that was out of the blue, just an exam problem. Right? The explanation that if you take a wire and you are moving it along in a constant magnetic field, what happens is the flux of the vector field of this B field, this magnetic field, changes when you turn. So when you turn this wire around, so this oscillates. So the rate of change here is non-zero, and that relates by this Maxwell equation with the flux of the curl of E. So you've switched from the magnetic field, the change of the magnetic field to electric field. This flux of the curl of E can now, with Stokes Theorem, be written as a line integral along the boundary of the electric field. If you have an electric field and you are moving an electron along in an electric field, this gives you work. So this is like a force pushing the electron. And then you can use this, you can put that wire on a bulb, like here, and then it produces light. There's another theorem, that's unit 24, it's the Divergence Theorem or Gauss Theorem. It deals in one dimension higher than this one. So we, instead of integrating over a surface, we integrate now over a solid. We write solid as E, and so solid is something different than a surface, right? This inside of this ball, that's a solid. We call this usually a ball. That's a solid, and the boundary is a surface. And in some sense, what this actually is, this theorem, it's a conservation law. Maybe I'll just illustrate this here with this kind of some kind of electric field leaving that. So what has been generated inside has to leave. But the first thing we have to do, like here, we computed the curl, we compute the divergence of it. So in this case, we had the divergence equal to 1. And actually, that's kind of just some remark I want to do. That's one of the nice things. If divergence is constant, you can actually often compute this triple integral just easily. And we know the volume of a sphere. We have computed that. I'm not doing that again here. We know the volume is 4 pi. For the right-hand side, what we have to do is we have to compute the flux of this vector field through the boundary. So in this case, we have to write down the flux integral. Let's just do that. So this is 4 pi third also. I was kind of abbreviating a little bit this integral here. This integral is 0, this integral was 0. This integral gives us then 4 pi third. Again, here also two remarks. Special cases if the vector field F is the curl of another vector field. You have the divergence of the curl of G. That was an identity that was 0. So in this case, this is 0 because you just integrate 0. On the right-hand side, what you actually have is a situation for Stokes Theorem. So in this case, we actually integrate the curl of G over the surface. But this surface, the boundary surface of a solid, never has a boundary. So that's very cool. When you have a solid and you take the boundary, this surface, this doesn't have a boundary at all. There's no end of the world. And what we have just seen here also in the example already, and we will exploit this quite a bit, the volume can be computed by just integrating over the surface boundary. Right? If you have a complicated object and you want to compute the volume, the only thing you need is to integrate over the boundary. Oh, I actually forgot something which is also related to fluid dynamics and the curl. This is a vortex gun which produces kind of a vector field which has quite a bit of curl. One of the great applications of the divergence theorem is to explain gravity in a more fundamental way. So Newton did that, and he kind of figured out that there is a 1 over r squared. But why is there a 1 over r squared force? Why is it not 1 over r cubed? And you can actually do gravity in any. Gravity is a big field. See that with a heavy book. You can do gravity on any space, even discrete spaces. You can do gravity on a 4-dimensional space. In 4-dimensional space, for example, the force is 1 over r cubed. But how do you see that? And one of the ways to see that is to formulate gravity more fundamentally. This equation of Gauss is much more powerful than Newton's equations for gravity, because what it actually tells you is that the mass density is the source for gravity. So it's the same equation, by the way, which you see in the Maxwell equation. Here it's just the charge density, here it's the mass density. And one of the applications is that you really can compute the force, for example, also inside the body. You can see how much gravitational field you have inside the Earth in distance r from the center. We will do that maybe in class, but you can also compute the force away in distance rho from a body. And in order to do that, we use the divergence theorem. So if you are in distance rho and you use a big sphere of radius rho around the body which you have, what happens is then the force is kind of just by symmetry, it's a scalar f of rho times a unit vector. So the gravitational force goes inside. We have a parametrization. Because the vector field is always perpendicular, that's what you do in the homework. You verify this is just the surface area times the strength. Surface area is 4 pi rho squared times the strength. Then you have 4 pi m is minus 4 pi f rho squared. The 4 pi falls away, and you get Newton's law, which says the force at distance rho is minus m over rho squared. And that's the end. This is the theorem, the last theorem. In class, we will then also look at an overview over all the integral theorems, and then we have concluded the course.